So today our speaker is Professor Alexander Rothkopf from the University of Stavanger. So Alexander is a full professor in physics at the University of Stavanger, and he is a member of the Young Academy of Norway. He received his PhD from the University of Tokyo, and he got postdoctoral position at the University of Bielefeld, Bern, and Heidelberg. Then he became a junior group leader and a scientific manager at the IsoQuant Center of Excellence in Heidelberg in 2016. And then he became a tenured associate professor at the University of Stavanger in 2018. He works on machine learning approaches to real-time dynamics of strongly correlated quantum systems, and his research is funded by a Young Research Talent Grant from the Norwegian Research Council. And today he will be talking about the heavy flavor in QCD matter and the lattice. Welcome, Alexander.
Thank you very much. A very big thank you to the organizers of this virtual seminar series and our host today, Claudia, for the kind invitation. It's a real pleasure to participate in this seminar series and to have the opportunity to tell you about heavy flavor in QCD matter and the lattice. Well, the enthusiasm to study heavy quarkonium, and this is my personal taking the liberty of somehow specifying the title to heavy quarkonium here. The enthusiasm to study heavy quarkonium in extreme conditions of temperature and density is shared by both the experimental and the theory community. On the experimental side, heavy quarkonium, the bound state of a heavy quark and anti-quark, turns out to be an actual precision probe in heavy ion collision studies. And the community by now has really put forward the high precision data to back this claim up. There's a clear experimental advantage, namely that one finds clear signals of the decay of these say the vector meson quarkonia via enhanced lepton decay channel. And just to pick some recent plots here, the iconic bothmonium spectrum and the suppression of the bothmonium family by CMS, and quite recently now the measurements of the J psi and specifically the psi2s, the excited states for the germanium vector channel family by the ALICE collaboration and CMS collaboration, now combined, giving a consistent picture here. And as you might have noted, I've snuck in some result here that is not a quarkonium result, but I'm quite excited about it nevertheless, which is the measurement of CMS of the X, so the double ratio for the X3872, which I think will be of quite some interest for the community. On the theory side, quarkonium provides a genuinely clean QCD laboratory, with the central theory advantage being that there is a inherent separation of scales present that enables powerful effective field theory tools. And the separation of scales that I'm referring to here is between the intrinsic scale of quantum fluctuations in QCD, this is so-called lambda QCD, and the heavy quark rest mass, as well as environmental scales such as the temperature and the heavy quark rest mass. And this separation of scales allow us to go over to a more intuitive, non-relativistic language for the heavy quarkonium. And we can start describing the in-medium behavior of quarkonium through concepts such as potentials or transport coefficients, and bringing both this theory and experiment together through phenomenology. We then hope to gain a quantitative understanding of both QCD in medium bound states. And once we've established this knowledge about QCD in medium bound state, then we can use these as, say, the standard probes, precision probes of the QCD medium properties in a heavy ion collision. And it is here, this is not the main part of this talk, but I would like to simply point out that the community has made really great strides over the past years to understanding the interaction between the heavy quarkonium and the surrounding medium in a genuine quantum fashion through the so-called open quantum systems framework. Of course, we are interested in quarkonium eventually in a heavy ion collision. And so we know how a heavy ion collision essentially progresses from the early stages just right after the incident of the projectiles, which is dominated by very strong coherent color electric and color magnetic fields. These fragment then into colored quarks and gluons that quickly isotropize and then form a locally thermal quark-gluon plasma, which expands hydrodynamically. It cools off along the way, and as it hits the transition temperature to the hadronic phase of around 156 MeV, colored partons have to combine into color neutral hadrons that eventually leave the collision region and are measured in experiment. And the life cycle of heavy quarkonium similarly proceeds in the earlier stages where there are partons around that carry a large amount of kinetic energy that allows to create a QQ bar pair that may shed some of its color quickly to form a bound state early on. These bound states then interact with the bulk medium. If they are deeply enough bound, they may survive. If they are not deeply enough bound, they may these QQ bar pairs may decohere and become decorrelated into individual quark antiquarks. At the freeze out, then either a surviving in medium state can transition into a vacuum state, or as we now know, also if you produce enough QQ bar pairs in the initial stages of the collision, then you might have a statistically significant probability for now decorrelated QQ bar pairs to come together to form quarkonium again at freeze out, which, for example, for charmonium at LHC is a relevant channel. Okay, in this talk, when making connection to lattice QCD, I will focus on this intermediate part with thinking about quarkonium in contact with a at least locally thermalized medium. We can, since the study of heavy quarkonium in heavy ion condition is connected with physics, with the open physics questions, I've just picked three fields here. The classic work by Matsui and Sass has kicked, or in 1986, has kicked off quite a wealth of work, all focused on an understanding of thermal bound states. So is it possible for a QQ bar pair to bind into a bound state in the presence of a thermal medium? We have questions about kinetic equilibration that nowadays we can answer in a fully quantum fashion using the so-called open quantum system framework, which is related to kinetic equilibration and transport. So how does a quarkonium state that is in contact with this medium exchange momentum and energy, and how is it able to plow through its surrounding medium? And just one aspect that might not be in focus most of the time, however, if you think about future colliders at much higher energies, then the special role that heavy quarkonium takes on at currently accessible energies is somehow lost, as the heavy quarks are not so heavy anymore compared to environmental scales. And we can think even about chemical equilibration of heavy quarks and heavy quarkonium. In this talk, I would like to focus on three types of studies that have been carried out by the community in the recent past. And the first set of works are interested in understanding heavy quarkonium physics through the viewpoint of a non-relativistic interaction potential at finite temperature. And we will look at both the standard lattice simulations and how they try to extract this potential, and another implementation of lattice simulations that you might not have been familiar with regularly, and this is classical statistical simulations. Then I would like to give a little bit of a review on some recent work on in-medium heavy quarkonium spectral, either directly computed in a fully relativistic fashion using lattice QCD, or using non-relativistic effective field theories, also in conjunction with lattice QCD simulations. And last but not least, there is one more type of studies that I think is quite exciting and interesting, and that is related to transport coefficients such as, for example, the heavy quark diffusion constant that we now understand is again connected to the study of quarkonium and even the study of the heavy quark potential. Okay, I have been asked to talk about lattice QCD in connection with heavy quarkonium, and so let me briefly give you a rough brushstroke picture of what lattice QCD is. In lattice QCD, we discretize space and time on a hypercubic grid. The gauge fields now live on the links in between the nodes of this grid as the so-called gauge links, and the light fermions in our system live on the nodes of this grid. And the standard way that when you hear lattice QCD, what you think about is so-called Euclidean lattice QCD, where this grid, this space-time grid, is formulated in a compact imaginary time. And what one then does is one numerically solves Feynman's path integral in this Euclidean time. And the reason for going into imaginary or Euclidean time is simply technical, that only if one does so, Feynman's path integral turns out to be in a form that is amenable to efficient simulation approaches such as Markov chain Monte Carlo. And so one generates gauge field configurations according to some Markov chain, according to a certain probability distribution e to the minus s, where s is the QCD Euclidean action. And then one estimates the quantum statistical expectation values by taking the mean. So you compute the observable of interest on each of your generated lattice configurations, and taking the mean systematically approximates the quantum statistical expectation value. The starting point, nevertheless, was that we had to go over to imaginary time. And since the physics, for example, of transport is decidedly a Minkowski time phenomenon, the drawback of this method that otherwise is fully ab initio is the costly return to the real-time setting. And we'll talk a little bit more about this later on. Then in the standard setting, you can either introduce heavy quarks as relativistic fermion fields, so you can place them on the same lattice as your light quarks. That for the heavy quarks to not fall through your lattice, you have to make your lattice very finely spaced, and that makes these kind of relativistic simulations of heavy quarks very, very expensive. And this is why instead people have are using the separation of scales that I mentioned before to separate the simulation of the light degrees of freedom, that is your gluons and your light quarks, that you can now simulate on a much coarser lattice, and you separate this physics from the physics of the heavy quarks or even heavy quark anti-quark pairs in an effective lattice theory that you evolve right on top of your standard Euclidean simulations. And this is what is called lattice non-relativistic QCD or NRQCD. I would like to bring up one more, and this slide is called the various phases of lattice QCD. So we had Euclidean quantum QCD with relativistic or non-relativistic heavy quarks. And now I would like to briefly mention that there's another lattice type of simulations that are real-time classical statistical simulations, which are formulated directly in Minkowski time. But obviously there must be a catch, and that catch is that one has to neglect all quantum effects in this theory. What one does is one draws a set of statistically fluctuating gauge field initial conditions, then evolves them deterministically, and then computes statistical averages of observables at some finite Minkowski time. This surely represents a approximation to the full theory of QCD, which which is valid at high occupancy, meaning in situations such as very early on in a heavy ion collision, the so-called Glasma phase, or for physics that is dominated very deeply in the infrared. And people have, for example, used this to investigate the dynamics of topology changing processes through so-called Sphaleron transitions. And again, taking the continuum limit is somewhat subtle in this, and you don't get, of course, any confinement physics in here. However, you can already get some insight about, for example, the interaction of a bound color anti-color charge in a very highly occupied environment. Okay, so usually, and the main part of this talk, I will focus on Euclidean simulations that are formulated in imaginary time. And I mentioned that, well, in the end, we need to get back to real time. And the way I would like you to invite you to think about this challenge is through so-called spectral functions. And you can think about Euclidean lattice QCD simulations as acting to a very imperfect detector or a very imperfect telescope if you're observing some star far away through your optics. And so what you're interested in is a spectral function here, for example, for the J-psi system, for the charmonium system at zero temperature or very low temperature. So you have your J-psi peak here, you have a psi prime peak here, and then the DD bar threshold opens up. And so this is the actual spectral function that QCD exhibits. And what does a lattice simulation do? Well, it takes this spectral function and it converts it to a so-called Euclidean time correlation function, which, is given by an integral convolution. And the convolution kernel here is usually related to an exponential function, so that at zero temperature, you get a correlation function in Euclidean time here that, if you look at these two lowest lying well-separated delta peaks, you can find them again here. If this is the log of this correlation function, you can find them as exponential fall-offs in this correlator. And so at very low temperatures, where you have a long reach in Euclidean time, you can often identify both the ground and maybe also some of the excited states and extract the masses in this way. Now, in finite temperature, the spectrum itself becomes less simple. Some of the structures that exist at finite temperature have been, let's say, gobbled up by the threshold that is moving downwards, and the vacuum bound states might broaden due to interactions with the thermal medium. And that means that you're now getting a correlation function out of your lattice simulation that does not exhibit these nice exponential fall-offs. And to add insult to injury, due to the subtleties of Euclidean field theory, actually the range in Euclidean time that you can simulate is actually limited by the inverse temperature. So the hotter your system gets, the less you can peek into the Euclidean time. And you can imagine that this makes extracting the spectral function from the simulated correlation function more and more difficult as temperature increases. And this actually is a so-called ill-posed inverse problem of extracting now the spectral function from this correlator. What the relativistic formulation that contains both structures at positive and negative frequency offers is that it not just encodes the physics of the bound states and the threshold, but it also actually can encode the physics of transport, so-called transport coefficients, which are defined from the low frequency limit of your relativistic spectral function. Okay, so if we are interested in transport, then we probably have to work with the relativistic formulation. But if we're only interested in the physics of the bound states, then this is where these non-relativistic formulations such as NRQCD, non-relativistic QCD come in, where essentially what one does is one redefines the zero of energy in your system, essentially introduces a chemical potential for the heavy quarks, and by that one shifts the origin of the energy by essentially 2 times the heavy quark mass. That means everything on the negative frequency side is completely neglected. It's shifted to minus infinity essentially, and you end up with a spectral function that now only includes at zero temperature, at least here, the bound state peaks and the threshold on the positive side of frequencies, and that makes the correlator that you get out of this not symmetric anymore, but it allows you to then get better access to these structures that are encoded in the spectral function. Nevertheless, it remains an ill-posed inverse problem. So even with the non-relativistic formulation, it is still a computational challenge. Okay, so how do people go about extracting this spectral information from correlation functions? And there's my personal work has focused on so-called Bayesian spectral reconstruction, which is a approach where one supplies additional prior information, for example, about the positivity of spectral function, to regularize this inverse problem. I'm sure you've heard about the maximum entropy method, which uses prior knowledge about positivity of the spectral function and makes sure that it does not introduce any additional correlations where there are none in the data to regularize this inverse problem. Or the BR method that I have co-developed, where we use the positivity of the spectral functions, we enforce twice differentiability of the spectral function and make sure that the results of the reconstructions are independent of the units of that spectral function. What they all have in common is that because this is an ill-posed inverse problem, careful analysis is necessary of the artifacts you necessarily introduce through the regularization of this ill-posed problem. And this is often then combined with a mock data analysis. And if you would like to know more, I've recently put out a small review on the topic. Then there's other clever ways how you can estimate spectral functions in the literature today. And one way is to use model spectral function fits. So you would go and come up with a realistic form of the spectral function with a few tunable parameters, often inspired by continuum computations. So for example, if you're interested in the spectral function, the in-medium spectral function of your relativistic theory, then you could, for example, model the shape of the bound states, of the in-medium bound states, using a prediction from a continuum effective field theory called potential non-relativistic QCD. And you can use other predictions from infrared effective field theories to make a ansatz for the shape of the transport peak, for example. And then you would combine these model ansätze for the low frequency and the intermediate and high frequency parts of your spectral function. They are described by a few parameters, and you then use these few parameters to fit this model spectral function to your correlator. Then let me just mention that there's work in progress where people are trying to figure out whether there are ways how to extract relevant physics, for example, transport properties, without the need to actually carry out a spectral inversion. However, so far, as far as I understand, this has only been achieved in very limited cases. So there's no such thing as a Kubo formula for directly extracting transport coefficients from a Euclidean correlator in general. Okay, now that I've shown you a few aspects of what is involved in reconstructing these spectral functions from the lattice, let me tell you about the first part of works that you can find in the literature on the heavy quark potential. So what is the heavy quark potential? Well, we use it to describe the simplest model system that we can think of when it comes to heavy quarkonium, which is infinitely heavy color sources. So this is not really quarkonium. This is an idealized system of a color and anti-color charge that is evolving in real time here. And if you describe a QQ bar meson correlator and take the mass of those heavy quarks to infinity, then you're exactly in that limit of static color sources, and you end up with what is known as the Wilson loop, the real-time Wilson loop, which lives on this rectangular contour that your charges trace out as they evolve in time. The central question we want to answer here in this context is, can the real-time evolution of these infinitely heavy color sources be understood via a Schrödinger equation that is via a potential? So if they are infinitely heavy, then we don't have a kinetic term. There's no p squared over 2m here. But then the Schrödinger equation just reduces to such kind, would reduce to such kind of relation. And well, slightly anticlimactic, in general, we know that such kind of a relation is not true, because in effective field theories such as potential non-relativistic QCD, there exist non-potential effects that are related to your color singlet infinitely heavy color source jumping from a singlet state to an octet state and then coming back to the singlet state. But we may still attempt to extract the potential contribution to the dynamics, which should be dominant, or there's at least arguments that it should be dominant at late real times, when all the higher order harmonics have damped away. And this potential, of course, has first been computed in perturbation theory by Mikko Leine in 2007 and was found to be complex. And the question is, can we extract such kind of a complex potential also from Euclidean lattice QCD? And this is where spectral functions again come in as a central tool. If we assume that such kind of a potential picture exists at late real times, then we can take our equation up here, turn it around, and define what we mean by the potential from this late time limit of the behavior of the real-time Wilson loop. Okay, I just told you that on the lattice, we don't have access to real-time quantities. So the only thing we have is access to spectral functions in principle. And So what you can do is you can then essentially Fourier transform your Wilson loop in real time. And the relation, that's the nice thing about the real-time domain, is that your spectral function of the Wilson loop is related to the Wilson loop by a Fourier transform. And you can then write this definition of the potential as an expression in terms of spectral functions. And that is nice, or I should say first, so this somehow looks a bit non-intuitive. What does this tell us? But if you for example, if you think about the spectral function being a delta function at some omega peaked at some omega 0, then what you would get from this ratio is that the potential would be just the position of this delta function. And similarly, if your spectral function is a peak, for example, a Breit-Wigner, then the real part of the potential is given by the position of that Breit-Wigner, and the width is given gives you the imaginary part of this potential. Let's see. This is nice that we can somehow relate the potential to shapes in the spectral function, but we still didn't say that we have access to them. Well, it is here that we now need to solve this ill-post inverse problem to then get access to the spectral function from our Euclidean time Wilson loop that we can actually measure. Okay, I now gave you some formula, and this is a bit quick. Let me show you some of the testing we've done. So before going to any lattice data, of course, we should test whether this extracting the potential from spectral functions and from correlators actually works. And the first tests that we did back in the days was that we took Wilson correlators from a hard thermal loop. So these encode a non-trivial spectrum, non-trivial spectral function, and a non-trivial potential, namely the potential that Mikko Laine essentially computed. And we test the whole pipeline. So here, what I show you is a plot of these hard thermal loop Wilson line correlators versus Euclidean time for different spatial separation distances. So if your Wilson loop is if the static quark and anti-quark, the color and anti-color source, are very close in space, then as Euclidean time progresses, not much happens. But if you make them sit farther apart, you can see nicely that there's some exponential-like damping here. This is a log scale. We are using here the Wilson line correlator. Previously, I talked about the Wilson loop. Why do we use the Wilson line correlator here? Well, the Wilson loop actually has 90-degree corners, and these 90-degree corners induce so-called cusp divergences, which actually lead to very large structures in the spectral function that are unrelated to the potential. And the Wilson line correlator in Coulomb gauge does not contain these cusp divergences. So this is the technical reason why we use these Wilson line correlators. Okay, then we can use our favorite method of spectral function reconstruction to extract the spectral functions from these Wilson line correlators. And just to give you some example here, I used 12 points, and we put 10 to the minus 3 relative error. We sorted this ideal data and then reconstructed the spectral functions. And you can see here 4 examples of the 4 lowest, I think, of these spectral functions. The gray ones are the actual spectral functions encoded in this correlator that you can compute analytically or semi-analytically. And the colored ones are the reconstructed spectral function using, for example, this BR reconstruction method. And what you see is that for different separation distances, this peak shifts in frequency. The position of this peak gives you the value of the real part of the potential, and the width gives you the imaginary part of the potential. So if that is the spectral function for the lowest spatial separation distance, you can see that there will be a jump in the values of the real part of the potential, and then not so much as you go to larger separation distances. And lo and behold, if we look at the real part obtained from this peak position, then we see that the reconstructed peak position very nicely reproduces this gray line, which is exactly the real part of the potential encoded in these hard thermal loop correlators. And so we see that already with 10 to the minus 2 relative errors in the input data, we are able to reproduce the real part, at least in this hard thermal loop scenario, very well. And that bodes well because with modern lattice simulations, you can get correlator data that has 10 to the minus 2 relative errors. Okay, so this was just testing. There was no lattice here. This is all testing to make sure that we know what we're doing. And the next step then was to actually extract this potential from actual Euclidean data. And so what we then did is we used Bayesian reconstruction method of Wilson line correlators in Coulomb gauge from standard Euclidean lattice QCD simulations in quenched QCD and in full QCD, and in full QCD, so this is 2015, these were still simulations with heavier than physical quark masses on ensembles with 2+1 flavors of light dynamical quarks. One example here of the lattice Wilson line correlator in Coulomb gauge, and you can again see that it shows these rather nicely almost exponential decays in Euclidean time, and the different colors denote different spatial separation distances. Then we did the spectral reconstruction, and I show you here an example of these reconstructed spectral functions. They have been shifted by hand in the x-axis for you to better distinguish them. But what you can see, so this is the spectral function for the smallest spatial separation distance. And then as we go up, you have larger and larger spatial separation. And what you can see is that you start off with a very sharp, well-defined peak. And as you go to larger spatial separation distances, you get broader and broader peaks, which in the interpretation that I put forward would indicate that there manifests itself a finite imaginary part of that potential from that data. And when we use this legacy lattice data, we do obtain these results for the real part and the imaginary part. Again, this real part here, they are all shifted by hand manually in Y for you to better distinguish each other. If you want to correctly renormalize them, they should all agree, they should all fall together, and they do if you renormalize them correctly. They fall all together at small distances where temperature is irrelevant. Okay, so what these studies in the past showed us was that the real part of the potential shows a gradual screening as one goes from the hadronic phase to the quark-gluon plasma phase in full QCD, and there were indications that there is a finite imaginary part present in these ensembles. Now, I would like to come to some updates on the heavy quark potential that to me still present somewhat of a mystery. And here the font didn't work out. This is some very recent work now where we carry out the determination of the heavy quark potential on state-of-the-art lattice ensembles with physical pion masses, NF equals 2+1, that previously have been used, for example, by the hot QCD collaboration to investigate the equation of state. So these are very high statistics ensembles. And one might think, okay, great, we can just go ahead and use the same methods that we used before to extract the potential, but there's a caveat. There is a, let's say, a clash of priorities. Namely, in order to approach the continuum limit very efficiently with these state-of-the-art lattice ensembles, the simulations use improved actions that are proven to move more quickly towards the continuum limit than standard, say, Wilson action. However, these improved actions may actually induce non-positive contributions in the spectra. Of course, in the continuum limit, these will go away. But at finite lattice spacing, there might be non-positive contributions to the spectral functions. And this is why we cannot use the standard Bayesian methods that are all built on positivity of the spectral functions. So what we did is we used 3 independent methods to extract the potential. So we cannot apply the BR method, but we used 3 other independent methods. We used Padé interpolation. So you take your Wilson, the correlation function, you essentially do a rational interpolation of your correlator data. Then you have an actual analytic function, a rational function that you can then by hand take from the imaginary domain to the real time domain. But as you know, the Padé is very finicky, and it requires very high precision data. But with the state-of-the-art lattice ensembles from hot QCD and also TUM QCD, it is nowadays possible to actually use the Padé for spectral function reconstruction. Then we also used model spectral function fits, where one uses a very clever trick to subtract off, again, parts of the spectrum in the UV that are assumed to be unrelated to the physics of the potential. That's the lowest lying peak in the spectral, and then model the spectral function with a Gaussian peak. And the third independent method is to model the spectral function similarly to its hard thermal loop form, and that is to assume a certain decomposition properties of the correlator that hold in hard thermal loop perturbation theory, but then you assume that they also hold on the lattice and do a model of the corresponding spectral function. And lo and behold, what did we find? Well, there's a little bit of a surprise, namely that both the Padé reconstruction of the real part of the potential and the model spectral function fits, they both show us as a result a real part of the potential at any temperature that agrees essentially within uncertainties with the zero temperature behavior of the real part. This is quite different from what I had previously seen in previous studies using quenched QCD and also legacy full QCD actions. And it is also very different from what our current understanding of in-medium interactions between heavy quarkonium and a medium would entail, as the phenomenon of screening is surely a part of the, or is part of the phenomenon that we expect, at least from perturbative arguments, to happen when you immerse a heavy quarkonium into a hot deconfined medium. On the other hand,
Alexander, sorry for interrupting. There is a question in the chat.
Sure.
Hai Tao Shu is asking whether there are any analytic calculations, for example, perturbative lattice calculation at extreme high temperature, showing that improved actions will induce non-positive spectra.
So the problem is the absence of proof is not proof of absence. I think the naive Wilson action is the only action for which reflection positivity has been established, and this is what one needs to establish to guarantee that there are no positivity violations. I'm not aware that similar proofs exist for any of the highly improved state-of-the-art actions. But I also don't think there has been explicit studies of these non-positivities in improved actions. For us, this was simply a empirical finding that when we investigate the effective masses, so the log of the ratio of these correlation functions, a fully positive spectrum requires these to be monotonous, but we found that these structures, they show non-monotonicity, and that is the only way that one can explain this is by a non-positive contribution, as far as I understood.
Thank you.
Okay, yeah, thank you for the question. Then what is still deepening a bit, maybe the mystery, or for some not, is that these hard thermal loop inspired fits, well, you could say if they use somehow input that presupposes screening, then there is also no, this is not a surprise that the outcome shows also screening, but the question here is how far around, or so how good of a actual fit these HDL inspired fits are, and this is something that we have to look further into. So what was, however, very surprising to us again is this result that both the Padé and the model spectral function fits do show this somewhat unexpected behavior of no thermal modification. On the other hand, if you look then at the imaginary part, so here it's the gamma, the width of this structure of this lowest lying peak divided by temperature, and you can see that it somehow grows with temperature. What I would like to mention here is that at the moment there is no, while this is surprising, there is no inconsistency at first sight. So our colleagues have, for example, investigated the color singlet free energies, which are thermodynamic quantities, and on the same lattices that we have used to extract this potential. And of course, they see a screening in the thermodynamic free energies. And that means that as you separate your Q and Q bar any further, they lose coherence, and it doesn't, there is no more energy to be gained from moving them further apart, because essentially the medium has already ended any relevant communication between the Q and Q bar. And there's, however, you can think of two microscopic effects that contribute to this, and one can be screening, and the other can be wave function decoherence. And this is something that we learned through the study of the open quantum systems, that if you have a strong imaginary part, then this imaginary part too can lead to an interference, so to say, of the interactions between the Q and Q bar, so that you can think of the thermodynamic free energies showing screening, even though your real part is still up and running, but you're losing coherence thanks to the imaginary part. And so
we have another question.
Oh, sure.
Sorry, by the end, sorry for interrupting.
Yes.
He is asking, the limit that defines the potential does not exist in the case of the Gaussian spectral function.
Yes, that's very good.
What is the interpretation of the peak position and width in that case?
Yes, thank you, Dibendu. This is a very good question, and I think valid criticism of our approach here, that the model spectral function fits that had been originally used a Gaussian peak. And in my early work with Yannis Bernier, we investigated what kind of spectral shapes would lead to a well-defined potential, meaning a potential that is time independent. And if you just use a Gaussian, you will get something that has a time independent real part, but you will see that it has a time dependent imaginary part, and that is not a relevant, that's not a well-defined time independent potential. What I can say is that these fits have been repeated using Lorentzian, so Breit-Wigner type structures that need to then, however, be cut off at some point, because you cannot integrate so a just one single Breit-Wigner is not a Euclidean correlator cannot encode a single Breit-Wigner peak. Long story short, we have, and my collaborator Rasmus Larsen has redone these fits with these cut-off Breit-Wigner peaks, and he finds exactly the same behavior. So I agree that there is one may discuss the validity of this Gaussian spectral function ansatz. The surprising result of a non-changing real part, however, also emerges if we use a different peak structure that is in line with producing a time-independent potential. Thanks for pointing this one out. Okay, so I think this situation, because it feels, or it is so very different from our intuition that we have had so far, it needs more clarification. And the first thing that we can do is to recheck our results on finer lattices. So far, we can see exactly the same outcome. Rasmus Larsen has reported on that progress at hard probes recently. I also believe that it is important to compare the results using different lattice discretizations, especially in light of these non-positive contributions. And this needs to be a community effort. This needs to be different lattice collaborations to focus on extracting this quantity to finalize the lattice message on the heavy quark potential once and for all. This is also work in progress. And we are, of course, revisiting quenched QCD, where we had used the BR method previously. And now we are using newly generated quenched lattices and deploy all the different methods that we have in the arsenal now to investigate what the outcome is. And at the moment, what we see is that the PADE actually shows screening in these quenched simulations, as does the Bayesian reconstruction. And so this is really puzzling to me, and we are sure to get to the bottom of this. But I believe that it requires all these 3 points to be taken care of. Okay, I'm already running late. Let me briefly mention one other study of the static quark potential using these classical statistical simulations, just because it's one of the very few direct real-time approaches out there. So here in real time, the spectral function is really just the Fourier transform of the real-time Wilson loop. So what does one have to do is, okay, we want to simulate a stochastic bath of gluons in which we insert a charge, anti-charge from the outside, and that modifies the, if you have a static charge, anti-charge, that modifies the nonlinear, so let's say nonlinear Maxwell's equation, the Young-Mills equations that describe the deterministic evolution of your gauge fields. And we recently then finally understand that what we have to do is that we have to take care of these charge anti-charge pairs in a modified Gauss law, and then we can really get a Gauss law that now says, okay, if you want to compare to electric fields, if you take the covariant derivative of your electric fields, then you actually have on the right hand side of that Gauss law, you have your charge and anti-charge sitting there where you place them. And if you do that, you now get access to the real-time Wilson loop. Mind you, there are no quantum effects here. This is really just statistically fluctuating gauge fields. But what you see is that you get a Wilson loop in real time with a damped and oscillating behavior. And if you think about what will happen when you take the Fourier transform of this, well, the oscillations will correspond to a position, the peak position, and the damping corresponds to a width. And again, what we do is we evaluate the Wilson loop spectral function for different spatial separation distances. And again, you can see that you're moving, the peak position moves to higher values, but as you make the separation distance larger and larger, it somehow starts to stay on the same value while it's widening. And that, at least in this classical statistics simulation, again, showed us that in this scenario, you find a screened real part and a imaginary part that grows with spatial separation distance, just as a reminder that there is something to be learned from these real-time simulations. Okay, I guess I have 5 minutes left. If the chair agrees.
5 minutes sounds good. Yes.
Okay, I will then not have time to talk about transport coefficients, but maybe if I can upload the slides, if you would like to take a peek there. I would like to talk a little bit about directly extracting quarkonium spectra, and here the community, telling you a little bit what the community has done. So one very interesting type of work is related to extracting them from relativistic simulations. So we want to model the spectrum. One wants to model the spectral function, for example, of eta C and eta B, and then fit this model spectral function to a continuum extrapolated Euclidean correlator on high resolution lattices. And here one stays within the gluonic medium only because, again, you need to make your lattices fine enough. How do our colleagues then model this? The UV part of the spectral function comes from high order perturbative computation that is carefully renormalized in the same way as, or matched to, the lattice renormalization. And then the remnants of the bound states, the threshold part of the spectral function, is parameterized using a computations obtained from a weak coupling potential EFT computation. There's no transport peak in this channel, so that allows one to focus solely on the bound state remnants, and then one takes a model spectral function that introduces a shift and a rescaling of the spectral function. And our colleagues here have then taken these, have continually extrapolated the lattice data, that's the triangles here, and then you can see that the model ansatz by fitting these scaling parameters and now allows them to nicely reproduce the correlator. And they do this for different temperatures, and then that is how they obtain insight into the spectral functions of that are a valid hypothesis for this continuum extrapolated correlator. So for charmonium at 1.1 to 2.25, you see there's nothing left essentially, but for bottomonium, so A-B, there is up to 1.5, one can still see some enhancement here of the threshold. Then there has been quite some work on in medium bound states using non-relativistic approaches, such as this non-relativistic QCD approach. Here I will blatantly self-promote some work I did with Peter Petrezzi and Seon Kim, but our colleagues from the FastSum collaboration have done very relevant work on this both before us and at the same time. And the first thing, if you do such kind of a non-relativistic effective field theory, you need to check your zero temperature mass splittings of the quarkonium states to see how well your NRQCD approximation works at the lattice spacing you're simulating. Then the first thing that we did is check the raw correlation functions. And you can see here a ratio of the in-medium correlator to the zero temperature correlator for the, for example, the 3p1 channel. And what you see is that as you increase the temperature, you see this upward bend. And then we try to model what needs to happen to the spectral function that this upward bend in the correlator ratio appears. And we could explain it by a negative mass shift of the ground state. So as temperature increases, the peak wanders, the spectral peak wanders to smaller energies or smaller masses. And after doing a careful study of reconstruction artifacts using different Bayesian methods, we try to extract the peak position directly from the spectral function. And what we came to conclude is that there is, for example, here for bottomonium 3s1, there is a small but statistically significant mass shift up to around, say, 50 MeV as you increase temperature into the up to 400 MeV. Then you see disappearance of the ground state peak. This was the latest results we had were consistent with those results of the FastSum collaboration. And we only found, so we found a negative mass shift, but we didn't have access to the finite excited states. And this is the last point I would like to make, that there has been some work by postdoc Rasmus Larsen, who is now with us here at the University of Stavanger. They have been modeling spectral functions with the PNRQCD model input. And what have they done? Well, they try to get access to the excited states of the quarkonia and to the quarkonia. And one of this is a signal to noise issue. If you have all the three, say the epsilon 1s, 2s, and 3s states, the physics of all of those in one correlation function, the higher lying states may be swamped by the signal of the lowest state. And so what they did is they tried to project out the ground or the excited state contribution to the Euclidean correlators using input from zero temperature potential models. In addition, they also tried to subtract off, making an assumption about separation of scales, subtract off the UV part of the spectrum that is assumed to be temperature independent. And then they modeled again the spectral function of the remaining in medium physics to be a Gaussian with a small delta peak to capture for potentially some width, some tail that a deviation between a Gaussian and a Lorentzian does. And what they found is then, contrary to us, that within the error bars, they don't see any changes in the in medium mass, even though some of their values also, at least for Y1s, lie below the zero temperature result, but not significantly below. And with that, I will simply skip over the last part and conclude. I hope to have shown you that lattice QCD can provide us non-perturbative and first principles insight into heavy quark and quarkonium in medium bound states in transport. Phenomenologically relevant quarkonium physics requires access to real-time dynamics, and for that we use spectral functions. The community has now entered an era of high-precision Euclidean data from state-of-the-art simulations, which one now approaches using either spectral function modeling or direct spectral function reconstructions. And quite recently, I must say, there were some unexpected findings that I believe still require community effort. For example, the apparent absence of screening in the real part of the in-medium potential, despite the fact that we see clear signs of screening in the free energies, and the absence of mass shifts in recent studies on His lattices. I think this is really a call for different lattice collaborations to actually collaborate more closely, so that we can provide our friends and colleagues in phenomenology and experiments really with the first principles insight that they expect of lattice simulations. And with that, I thank you for your attention.
Thank you very much for this very nice talk. We have two questions in the chat still. I will ask the people who type them to unmute themselves so that they can ask directly. One still from Dibiendu, following up on the question that he had asked before. Dibiendu, do you want to unmute yourself?
Oh, hello.
Hi.
Hello.
Hi,
Hey,
Alexander.
Dibiendu.
Thank you for the nice talk. So I got your point, but the Lorentzian spectral function that you are talking about means you cannot do a Laplace transformation of that, and therefore you put a lower limit on the spectral function.
Yes.
And the result is highly dependent on the lower limit. So how can you say that is a valid spectral function?
So if I understand my colleague Rasmus correctly, he tried different ways of how to cut this Ansatz, this Lorentzian Ansatz. And what he can see is that this affects somehow how much width you assign to this Lorentzian peak, depending on where you cut it off. But it does seem to not affect strongly the position of that peak, depending on where you cut off this Lorentzian. So I agree that there is a dependence of the end result in the choice. However, also, and that is something that I think my colleague would now like to mention, that if you want to interpret the outcome really as width of width of a spectral function, then yes, these cuts do change the assignment of area under the peak. However, if you think of it in terms of the cumulants of the spectral function, then actually what you will find is that the second cumulant, which is somehow a summary quantity for the physics of this width, will remain quite unaffected by this choice of the cutoff. So I think at least for the question of determining the real part of the potential, I don't see that there is a strong dependence on this choice of cutting off. But this is definitely something that one has to be careful about. What are the admissible spectral features to assume? And I guess that is the benefit of the Bala-Datta method that lies behind what I called the hard thermal loop inspired fit, that it contains a spectral function ansatz that one can actually integrate up.
Yes, maybe one comment on this STL inspired fit. So you said that there is some predefined assumption of screening in that fit form, but I would like to correct that there is no predefined assumption of screening in the fit form.
Okay, I take the criticism. Yes, what I meant was that there is an assumption of a decomposition property, and indeed that is not the same as an assumption of screening. Thank you for clarifying this.
Okay, thanks for the answer.
Sure. And there's a long question or comment.
Right, that's right. Do you want to mute yourself? And
you can obtain the spectral function by simple Fourier expansion and
yes, I can talk myself. So
yes, thank you.
So if I understand correctly, the key challenge for you is that to obtain the spectral functions from some Euclidean propagators, right? And there's a very well-known conclusions in the thermal field theory that the spectral function is just the imaginary part of the analytical extension to the Matsuburg propagator, which is just the Euclidean propagator represented in the frequency space. So in principle, you can do a Fourier expansion to your Euclidean propagator, and then you do the analytical extension, and then take the imaginary part. Then you got your spectral function. So why this method has never been mentioned? Or
actually, I think what you're describing is exactly what the Padé approach is. The Padé approach actually is not applied directly to the Euclidean data, but it is actually applied to the Matsubara correlator. So you take your Euclidean correlator, you carry out a discrete Fourier transform that brings you to a lattice Matsubara correlator. You then do a rational approximation, which is then your, let's say, the closest thing to having the Matsubara the Matsubara correlator on the lattice. And then this, of course, is a function now of the imaginary frequencies, omega n, and you can then simply replace that argument by I omega n, and take the imaginary part of what comes out. And that is exactly what you described. Very well captured. So this is exactly what one then does. The problem there is that there are different ways how to obtain this Padé approximant. We use an interpolation formula because that does not require you to solve some optimization problem. Often a Padé approximation, you would have to somehow iteratively find the Padé coefficients from some minimization approach, and that usually is numerically rather unstable because you have these very high, so you get a lot of cancellations happening between your numerator and denominator if you use a large Padé or a high order Padé. And so we use an interpolation formula, but there the problem is that you're not just interpolating the true correlator, but you're also interpolating the error, the statistical error that's added onto the ideal correlator. And so then you're analytically continuing the actual correlator plus something else. And if that something else is not very, very small, as it is in current state-of-the-art simulations, then you get very quickly very large artifacts that then don't allow you to make sense out of this analytic continuity. But this is very nice that you brought this up. This is exactly the idea with the Padé approximation.
Okay. Thank you for your explanation. So my second question is that
sure.
You mentioned several times that the positivity of a spectral function is very important, right?
Yes.
When extracting your potential or spectral function, the positivity is very important. However, I learned from some literatures, I actually listed in this comment chat window, that the gluon spectral function in the confined phase can be negative. So the positivity is violated there. So I just wonder when can we use the positivity and when we cannot?
I should have been more clear and said hadronic spectral functions. And I should even be even more specific. Hadronic spectral functions of correlators with the same source and sink operator. So in the zero temperature, our colleagues that are doing high precision spectroscopy, they are improving their signal to noise ratios in their spectroscopy analysis by actually combining correlation functions of, for example, if they want to measure meson masses, where they use slightly different interpolating operators as the source and sink operator. And there too, you're not guaranteed that the spectral function is positive. So there's a small subset of relevant hadronic spectral functions that are positive definite, but this is crucial because positivity reduces an enormous amount of oscillatory zero mode, so to say. And there was some recent nice work by colleagues from FIAS who actually analytically analyzed the structure of these zero modes that can swamp your spectral reconstructions. And if you're not in a positive definite setting. And so this is really the key to many of the past successes of spectral reconstruction, that we were able to restrict ourselves to positive definite spectrum. And my group is, for example, working also on devising methods for non-positive spectral functions. And there has been quite some work also by the Heidelberg group on, for example, these gluon propagator reconstructions. And you have to work very, very hard to make sure that you somehow can avoid these oscillatory non-positive artifacts otherwise.
Okay, thank you very much.
Sure.
We have a question by Yin.
Okay, yeah, thank you so much for the presentation. Actually, I have two questions. One question is about the screening. And so I'm only speaking, I'm not expert, but my impression is people always using the potential as the input to do the say the JPSI phenomenology in heaven collisions. And that's so my first question is, does that mean actually people need to use the updated lattice results and reduce all those phenomenological analysis? So that's my first question. My second question is related to the next seminar, which I assume people will talk about the spin density matrices for the JPSI, which can be measured in LHC at least. So my question is, can actually lattice also lattice also got some information about in the median, how does the spin density matrices of say JPSI, because JPSI is spin one particles, how does the density matrices looks like in the median? Yeah, so that's my second question. Thank you.
So maybe I can start from the back. So far, the phenomenology, at least the fully quantum open quantum systems phenomenology, when it is using a potential, it is still using the static potential, so usually the lowest order of the potential. So it has not incorporated spin-dependent corrections to that potential. But in principle, a master equation, an open quantum systems master equation for a QQ bar can be amended by such kind of a spin-dependent potential, and you could investigate how then different say p states are affected. On the lattice, if you use NRQCD, so this lattice effective field theory non-relativistic QCD, the whole spin structure of your non-relativistic two-component spinor is present, and you can ask for if you use NRQCD to order, say, v to the 6, that is so the expansion. You take the expansion of behind this effective field theory to high enough order, you do get spin-dependent effects also included in the interactions, and that in principle can give you access to correlation functions projected to certain spin states, and should include so you should be able to construct observables that make explicit reference to the spin degrees of freedom. So this should be possible. I personally simply have not focused on that line of inquiry myself. Then coming to the question about the potential, so extraordinary claims require extraordinary proof, and I think I would like to clarify first what is going on with the quenched case and these methods to really make sure that we have all possible artifacts in this spectral reconstruction under control. If it turns out that by generating extremely high precision ensembles, the previous results become superseded because we got it wrong before, at some point one would have to redo the simulations. But at the moment, I am not yet fully at the point that I would say that I would bet my house on this real part, but it is there. We've been trying a lot to poke holes into it. We are not able to poke holes into it, as any good scientist should do. And so, yeah, to me, this is something I still need to better understand before I would ask a graduate student to redo all of the simulations previously done with a screened potential, now with an unscreened one.
Thank you.
Thank you so much.
Thanks.
I don't see any more questions, but I have one myself still about this issue with the real part of the potential.
Sure.
Or some. I was wondering, so the result that you showed from 2015, what's the pion mass there? And
300 MeV.
Oh,
so
okay. So it's not so heavy. So, and there you see still the real part changing with temperature.
Yes. So so at least the hotter the temperature, the less reliable the reconstruction, because the access to physical Euclidean time range diminishes. So even if you have the same number of points in tau direction, the physical length is diminished. I've, together with my collaborators at that time, we've done a lot of consistency checks and tried really to somehow make sure that we are not overlooking any systematics in the spectral reconstruction, because there's always two things. Your spectral reconstruction depends on the statistical uncertainties and on the regularization. And so we've tried a lot to change the regularization parameters and included that in the overall error budget. And that's the best due diligence we have. And here we clearly see a nice gradual screening. What was very consistent was that when we looked at this in quenched QCD, we would actually see that below TC, we don't see any change at all. And then as you go into over the actual phase transition that exists in SU3, then you would see a significant change in the behavior as you go into the deconfined phase, which again was somehow consistent with intuitive, what you would intuitively expect to happen, and what the difference between dynamical QCD and quenched would also be.
Okay. Now we have a raised hand from Minhe. Minhe, do you want to ask your question?
Yes, thanks. Hi, Alexander. Thanks for your nice
Hello.
presentation.
Hi, Minhe.
Yeah, very impressed by your talk. In the last part of your talk, you went over the possible mass shift of heavy quarkonia.
Yes.
Yeah, one study by R. Larson, was
Yes.
the mass shift may be very, very small or no mass shift at all, right? Which is of course consistent with the finding that the heavy quark potential, the real part of the heavy quark potential, was nearly not screened at all.
Yes.
But you also showed a study, probably by yourself, that there was a mass shift on eta C and eta B.
Yeah,
negative mass shift, right?
Yes.
Yeah. So how was this mass shift, negative mass shift obtained? And
so
what's the difference between its two approaches?
The difference here is that in our case, we actually reconstructed the spectral function using Bayesian reconstruction methods. Actually, 3 different Bayesian reconstruction methods, and then we used If I go into more details, it becomes a technical exploration. The thing is, you take the correlation functions you get from the lattice, and you just do the Bayesian reconstruction on it, and then you extract the position of the lowest peak. And we use the standard current correlator from NRQCD for this. While in Rasmus Larsen's, they modified the correlator by projecting it to the ground state, first excited or second excited state contribution, using these potential model wave functions in the sink and source. So they use a different correlation function. In addition, they also cleverly subtract a UV contribution that they assume to be temperature independent. And they do not use a Bayesian reconstruction method, but they use these Gaussian model spectral functions to estimate the position of that peak. And so there's some difference in both the underlying correlation function and the way how to extract this peak position in between those 2 studies.
Okay, so here not only for ground state but also the side state 2s and 3s have no mass shift, right?
Within statistical errors.
Sure. In your study, you did the ground states.
We only have ground states, yes.
Yes.
So that was the limitation of our approach. That if we don't want to touch the correlation function, then that's the only thing we have a chance of extracting. And what Rasmus did was he thought about how can we distill the physics of the different states separately to then investigate their in-medium behavior. But that means that one is using 1 or 2 additional steps of pre-processing before extracting the position. And there's in the paper, all the steps are justified and argued for. So therefore, I think this is what I meant with, we have to clarify the situation that we have results on the one hand that indicate that there is a mass shift and that there is screening, and we now have new results that claim, okay, we don't have screening in the potential and we don't have mass shifts, and we simply have to figure out what's going on. And sure. We are at work to hopefully soon give you more updates on this. Yeah. So there's also a follow-up study on this paper here from 2020 in the works.
Okay, thank you. We look forward to that.
Thanks. I will convey this to my my colleague Rasmus.
Thanks.
Okay, so I think we are out of time, and I would like to thank Alexander Rothkopf very much again for this very comprehensive and nice talk. Thank you all for staying with us until now, and I would like to invite you all for next week, a topical discussion on vector mesos spin alignment in heavy ion collision by Subhash Singha and Luca Micheletti. Thank you. See you next week. Bye-bye, everyone.
Thank you, everyone. Bye-bye.
Bye.
Thank you.
Bye.
Thank you.